Thanks for the introduction. So today I'm going to talk about this new work. The manuscript might show up sometime soon, and we also had a patent on this. So this work was done in collaboration with Tomas Jochym-O'Connor at IBM and Arpit at Caltech, Maissam, Barkeshli, UMD. So the motivation of this work is that we know typically one needs costly matrix state distillation protocol to achieve universality for 2D topological stabilized code. Some alternative is one can use a non-abelian topological code such as Fibonacci trivial code to achieve a universal gate set via braiding non-abelian aliens. Actually, we also have some work on that. But however, the error correction and the decoding protocol currently is still very sophisticated, and so it's less well developed compared to the stabilizer code. So you might expect the fidelity and the threshold to be low. But somehow there's an alternative approach, use this so-called just-in-time decoding discovered by Bombing and later also implemented by band to surface codes to simulate the non-Clifford gate in the 3D color code or surface codes using 2+1D space-time. However, it's unclear whether there's a well-defined 2D stabilizer code space at each moment. Also, the threshold of this decoder is relatively low. The phenomenological noise model is about 0.1%. So our question is there a way to perform a non-Clifford gate in a more intrinsic to this stabilizer code with a threshold that could be close to the standard surface code threshold? So to begin, we first introduced the 3D surface code. So it has a lattice model, have two types of stabilizer, the X stabilizer, which is living on the vertex, and the Z stabilizer living on the placate. And there are also a more continuous topological quantum field theory picture that the error or the excitations associated with this model either the E particle or the M loops. So if you apply a Z string, you create two E particles at the end, and then if you apply an X membrane operator, so you create a loop like an excitation. So what's also important is the boundary of this model. So there are two types of gap boundary. So one is called the E particle condensed boundary, where the E particle can disappear on this boundary. So it corresponds to the Z string can terminate on this boundary. And similarly, there's a M string condensed boundary, where the M loop or string can disappear on this boundary, and it corresponds to the termination of an X membrane operator. So the logical operator in the 3D surface code can be seen as a Z string on the edge of the original lattice, and then the logical X is this vertical X operator on the edge. In the dual lattice picture, it looks it's on the face, and it looks more like a membrane. So then here is the continuous picture. You have a Z string intersect with the X membrane at a single point. So then we can apply logical CCZ gates in the 3D surface code with the transversal CCZ. It's first discovered by unfolding the 3D color code by Kopika, Yoshida, and Pastovsky. And then it was realized directly in the 3 copies of surface codes transversally by Maissam and Braun. So this is the picture of the setup. You have 3 copies of a 3D surface code aligning X, Y, and Z directions, such that the logical X membrane intersect at a single point. So satisfy this condition, and such that you can have a logical CCC gate. So now, in order to understand how to do these gates in 2D, we just have some warm-up to understand first the physics behind this logical gate. So as first pointed out by Benny Yoshida, and then later also Webster and Bartlett, and some of our own paper, that there's a correspondence between the action of a logical gate, U, or it's also some emergent symmetry of the code space. It's equivalent to sweep the corresponding defect omega. So if you apply a symmetry or operator here, then at the boundary you create some defect. And if you switch this defect across the whole system, you are applying this global symmetry, which is a transversal gate, and then the defect also disappear on the boundary. So now you know that there's an additional condition that, so if it's a logical gate, so this defect need to also condense on the boundary. So that's a physical picture. So in the context of this model, there are two important defects, which are called CZ and CCD defects, which are also described in these papers. So you can consider stack code, which is 3 copies of toric code, we just explained. But then it corresponds to, in the field theory, topological quantum field theory picture, it's equivalent to a Z2 times Z2 times Z2 gauge theory. So there are two types of so-called gauge SPT defects. So this SPT stands for symmetry protect topological order. And this connection was first realized by Benny Yoshida. So one defect is a codimensional 2 defect, which lives on a string. And so the symmetry operator corresponds to this defect is living on a codimensional 1 submanifold, which is a plane. So which it corresponds to a CZ operator. So there is a defect fusion rule that if the M string cross this CZ defect denoted by S2, so S stands for SPT, so you will get attached by microphone? Okay, sorry. So yeah, Fortunately, my classical computer is for torrent. Yeah, so yeah, sorry, it's hard for me to point to this. Yeah. Okay, that makes more sense. Sorry. Haven't opened this feature. Okay, sorry. I mean, maybe I'm continuing with the laser. It's fine. So here's work here. So there's a CZ operator, and it intersects with this X membrane, so which will source a Z string operator. So it performs a logical CZ gate. And recently, we also clarify the underlying topological physics, which is using the TQFT formula that you can write this defect, the word sheet of this defect with a path integral, and this E1, E2 correspond to the gauge field related to the E particle. So it's kind of clarified in this paper. And also we apply this kind of formalism to the study of higher symmetry gates in the LDPC code, just the paper appeared last week. So the other defect, a codimension 1 defect, which lives on a membrane called the CCZ defect S3. So it has a more interesting defect fusion rule that it maps an M string to a product of M string times the CZ S2 defect. So there's a hierarchy structure. And then if you look at the operator picture, it means if you sweep this defect, it's equivalent to apply transversal CCC, then you will source a CZ membrane that is parallel to the X membrane. So if you sweep to the whole system, then you apply this mapping, which is a mapping of a CCZ operator. And similarly, you could also write down a TQFT formalism that, by the way, this is a cup product, which is a discrete analog of the wedge product. And this expression finally has a relation to that all the 3 type of X membranes has to intersect at a single point. So this cut product, the meaning behind it is the intersection of the operators. From the category theory picture, these defects are so-called condensation descendants of the E particles. They are all can be considered as a condensation of E particles in certain ways. Okay, so then in some one of our previous paper about a fractal topological code, we find a new type of boundaries. In that paper, we call exotic boundaries. I mean, here we rename it as a magic boundaries. So it's magic in the sense that it's not it's outside a stabilized formalism. So the CCT defect actually does not condense on boundary on 3 copies of M boundary or 3 copies of smooth boundaries. But it generates an exotic boundary. So if you apply the defect fusion rule before, introduced in the last slides, so it creates this some sort of a new condensation of the excitation, which is the M string together with the CZ defect can condense on that. So we can understand this magic boundary to be a composite boundary, which is a defect attached to the 3 copies of M boundary, like this. So then you ask about its condensation property. Then if M pass this CCZ defect, then it gets another CZ defect attached. So that thing cannot condense on the usual M boundary. So that tells you that the M string could not condense on its boundary. And the E particle could also not condense this boundary because if it passes the defect, it still remains itself and it cannot condense on the M boundary. So, but instead, a composite of the M string and the CZ defect, when it passes the CCZ defect, it just transforms back to the M string. Now it can condense on the M boundary. So the answer is you can condense this composite object. And in the operator picture is that the product of X operator and CZ operator can terminate on this so-called magic boundary. And it's beyond the usual picture of a Lagrange subgroup of a gap boundary. Okay, so now we can also consider how to construct an exact lattice model of these magic boundaries and also the bulk of these 3 copies of the toric code. And that's due to Maissam and Brown. And so basically, this picture might look complicated, so it doesn't matter if the details doesn't matter too much, but let me try to explain. So each dot corresponds to 3 qubits. So it's actually 3 copies of toric code. And the stabilizer in each copy is a volume or 3 cell with these 3 different colors respectively. And the Z stabilizer in each copy is given by the phases at the intersection of the complementary 3 cells. So for example, for the first copy, which corresponds to the X stabilizer to be the yellow, and then this square, the red and blue square, which is the intersection of the blue and the red cells, will be the Z stabilizer. So that's the construction of the lattice model. Now we can also construct 3 copies of M boundary by truncate the 3 types of X stabilizer on all the 3 copies of the 3D surface code. And then when you apply the CCZ gate, you create this kind of magic boundaries. So we can understand this first in the bulk. So if we apply the CCZ to the X stabilizer, so it becomes a product of X stabilizer times a CZ operator with the same support. And now what's important is in the bulk, this CZ operator is a logical identity. So one can understand this by, it turns out the intersection between, the mutual intersection between this X cell, of these 3 X cell has an even number. So what it means is if you apply the CZ operator on one of the X stabilizer, then you get an additional Z operators at the intersection. And the Z operator will only intersect with the other type of X stabilizer in the other, in the same copy with even number of times. So they commute. So that's why it's a logical identity in the bulk. So however, when you truncate this boundary, then this intersection becomes an odd number. Then so this CZ is no longer operates no longer a logical identity. So you cannot just get rid of it. So in the bulk, you still have the original X stabilizer, but on the boundary, you will get this XCZ stabilizer. So it's kind of a non-poly stabilizer model. And also keep in mind this non-poly stabilizer only commute with each other when you project to the code space. So in general, when there is excitation, they don't necessarily commute. So it's not very easy to directly do error correction on this non-poly stabilizer model. Okay, so now we have the basics physics explained. Now we consider how to construct the 2D stabilizer code. So the idea is you compactify some 3D topological code or topological order into 2D. So by compactifying, compactification just means reduce one of the dimension to constant, to order 1 length. So I can compress this 3D surface code with both sides with M boundary, or it's smooth boundary. If I compactify it, it gets this thing which I denote by M bar M, so which means upper and lower side are both M. And that's nothing but the 2D surface code. Just look at the lattice, it's just 2D surface code. But then if you have a E boundary on top, M boundary on the bottom, if you compactify it, you get this E bar M patch, and we call it a nail board because it looks like a nail board. And turns out this nail board is no longer the 2D topological order or 2D surface code. It is a trivial phase, which means it's constant depth equivalent to a product state. If you apply constant depth circuit, you can connect to a product state. So we can see why this is true. So basically, this model has Z stabilizers on the square and also on the vertical 3-body placates, truncated placates. That's the Z stabilizer. But then there's the 5-body X stabilizers, which is the truncated X stabilizer on one side. So if you prepare all the qubits in the 0 state, so all the Z stabilizer will be automatically satisfied. Then you could measure each 5-body X stabilizer. So if you get -1, you can immediately apply a Z correction on the nail. So then you will fix this stabilizer just by a local correction. And this can be turned into a local conditional unificate. Instead of measure it yourself, you can use an ancillary to measure it, and the ancillary doesn't have to tell you the measurement result. Just apply a conditional correction if it's violated. So that shows that it's actually trivial. So also, there is a physical implementation of this compactification process. Is you could if one side of the patch is the M boundary, then you can always just measure out the bulk in the X basis. So in both cases, then you throw away these qubits, you get this patch. Okay, so now we want to introduce our code, so which we call this Kirigami code by a cut plus fold process. So first we dig a hole with an M boundary inside, and then we make this hole very large until it touches the external boundary. That is equivalent to a compactification process. So on all 4 sides, you just get the M bar M, which is just a 2D surface code or 2D torical. So 2D surface code live on a cylinder. So your original X membrane operator now becomes an X string operator. And the Z string is still a string. But what's funny is that on the top, there's this nail board, and there's still a membrane operator survive. So they are living on this dangling edge. So that's the code you get. And you can take 3 copies of them such that the nail board on the 3 different sides. So then you fold it into 2D, then you get a 6-layer 2D code, which you can also deform the topology. It's, the geometry doesn't matter. As long as the topology is the same, it's the same code. And there's a further simplification. So instead of using all the 6 sides of this compactified or the thin shell of this 3D cube, we can just truncate the only keep the 3 sides, truncate the other 3 sides because they look basically the same. The opposite side looks the same. So, but that will give you additional 1D boundary. So then when you fold it into 2D, you just get these 3 patches. So each patch contains 2 surface codes and 1 nail board. Okay, so then you might be curious about what the lattice looks like. So that's a bit complicated, but let me just show it roughly how it looks like. So remember that our lattice model is a bit asymmetric. So there's a yellow, red, and blue X stabilizers. So on one of the surface, we call surface A, which has this label. So this yellow part is just the nail board I showed before, but now the qubits are defined on the vertices instead of the edge, but it's the same thing. So then this is corresponding to the 2D model when you only keep the top layer. So how we obtain this model, we can just measure out the X qubits, the qubits on the bulk in the X spaces. So similarly, you get the M bar M for the red part and also the blue part. So they turns out to be a square outcome surface code. So then the other surface B, so due to the asymmetry, it looks a bit different. I mean, these are just technical details. So the blue part now is corresponding to the nail board, and then the yellow part and the red part correspond to the surface code. Okay, so that's how you can obtain this lattice model. So now come to the protocol to finally how to do the logical CZZ operation. So the basic is to follow, we want to follow this dimensional jump approach proposed by Bombing, so which we'll first use for code switching between 3D and the 2D surface code. Basically, you want to measure out the bulk, and effectively that measure out the X membrane to only an X string on the boundary, which is 2D surface code, and then you preserve the logical information. So how do you do that? So basically, when you do dimensional jump, you know the bulk of the wave function is a superposition in the X spaces is a superposition of closed loops, which are the word line of these E particles. So so on this loop, it has the minus sign. So if you measure out the bulk, you are like taking a snapshot of the superposition. You just get one snapshot. So in the bulk, if there's no errors in the bulk, it's all closed loops. But this loop could terminate on the boundary. So then on the boundary, you will get alien excitation, the E-particle excitation. So you need to make a correction on this yellow dashed line on the Z correction to recombine this alien. So then you effectively can map this 3D code to a 2D code. So when there's a measurement error or Z errors in the bulk, then you just get some broken string. But you can first apply a matching algorithm to fix them, and then you apply this correction on the boundary. So that's the basic idea. 2 minutes? Okay. So, sorry, I lose some. Okay. So now we want to apply the transversal CZZ and dimensional jump on the Kirigami code, which we can visualize still dig a very large hole in the bulk. So if we apply CZZ everywhere, then remember we just get this CZZ defect attached on the boundary to create this magic boundary, which has this XCZ stabilizer. So now you have to map this code back to the original code space. So, but you can understand this magic boundary from an alternative point of view. So if I still measure the original X stabilizer, so then this non-poly stabilizer is just equivalent to Z errors or E-particle excitation everywhere on the boundary. I mean, the physical origin, as I said before, is this defect is a condensation of E-particles. So then this is bad because you could have these guys occur with order 1 probability. So they could connect it to be a large string, and then if you apply the matching protocol, you could induce a logical error. So now the idea, so now we have to fix this problem to fix this order 1 distance, effective distance. So here is the idea. So instead of applying the transversal CCC in the entire region, we just apply on a quadrant, a box region that the size is just 1/2 the original length. So when you apply a transversal CCZ, you effectively create this CCZ defect on the boundary of the box. And also when it's attached to this big hole, it becomes this magic boundary. So as we said before, that it's equivalent to lots of E particles just occurs on the boundary of this box everywhere. So now we need to fix these errors. So fortunately, you can use a minimum weight perfect matching protocol. So the trick is that you put all the edge in the decoding graph inside this box to have 0 edge weights, such that they get effectively identified. So all you can think this whole region is kind of squashed into a single boundary connect to the E boundary below. So this whole region is identified to either a single point or to a boundary. So then all the excitation in the box, remember they are quite local, so they can only live on this boundary of this box. Now they will be automatically be put down to the bottom because there is 0 edge weight. So, and that won't induce any logical error because they will just locally appear in this region. So, effectively you will get the codistance reduced to d/2 because if you have an error with length d/4, then it may cause trouble here because there's nothing here to prevent it to be pulled down. And also because there's a single shell, so this matching problem is effectively equivalent to a matching problem on 2D surface with boundary. And so the phenomenological threshold is just like 10%, it has a high fidelity. So now you, once you measure out in the bulk, you project it again to a Kirigami code. It's just, by the way, so the bulk here, because we have very large holes, so bulk just means you create slice, you measure out a very thin slice. So originally we will begin with like 2 layers per topological copy. Now you end up with 1 layer per copy. So that's what measuring out the bulk means. So now again you have a Kirigami code, but you have all this excitation still living on the boundary. So this is a picture of 1 copy of the surface code, a Kirigami code look like. So now the next step is you measure out all the region outside of this box region. So then you get a smaller Kirigami code with a d/2 distance, but you effectively clean up all the errors. So then you end up with a Kirigami code that has 1 layer per copy. So there are 3 layers in total. And it's with a d/2 effective distance and effectively map back to the original code space, except that it becomes smaller. So now, of course, you need all the time to grow, all the d time to grow back to the original size. And we can finally check whether the logical operator mapping makes sense, that it is indeed a CCZ gate. So here's the warm-up. So if you consider the simplified picture when there's no holes, you apply CCZ everywhere that maps the X operator to X times the CZ operator in the other 2 copies. Then we do the dimensional jump. So slightly different from bombing is that we not only keep the surface code patch, but also the nail board. And then on the nail board, the X operator is still survive as a memory, and then the CZ memory still survive. So it's acting on the 2nd and 3rd surface code, although the first copy is a nail board. And then we check the Kirigami code. We notice that if there's an X membrane get intercepted by the whole boundary, then and also the box region, then the X membrane will get attached by an additional CZ operator restricted in this region. And then when you measure out the bulk, so the one CZ operator that survives is the one in the region of this nail board, because the X operator still has a membrane shape. And then you can measure out all the side region, that indeed you get a smaller Kirigami code, but the original X becomes X times CZ. So then you check that indeed a logical CCZ occurred. And then you can also do code switching to the 2D surface code by measure out this nailable patch or apply a constant depth circuit to grow it back. Yeah, here's the summary. So we use a compactification scheme to construct 2D topological stable code, which is the Kirigami code from 3 copies of the 3D surface code. And then you can do universal fault-tolerant logic gates with this 2D model with order D time overhead, because you need to grow them back to the original size. So the threshold of this protocol should be close to the 2D surface code, at least for the phenomenological noise model. I mean, the CCZ circuit might make the threshold more complicated. That's for future numerical study. So, so the outlook is whether you could also apply similar trick to quantum LDPC code. Okay, so thanks for your attention.
Hi. So you say that the threshold should be close to the threshold for the 2D surface code. But so you said for phenomenological noise, but then in the slides you said 10%.
Well, that's just for the dimensional jump protocol.
Right.
But the main threshold will be determined by the memory, which is just the 2D surface memory threshold. So this is just one part of for the applying the gate, you have a part to cleaning the error, and it turns out to be much higher than the phenomenological error threshold for the memory. So you don't have to worry too much about that. Yeah, I think that's potentially the main advantage compared to the just-in-time decoder, which the threshold turns out to be low.
Yeah, but so the threshold on the JIT decoder comes from measurement errors, right? Not from, I don't know. Maybe we can talk about this.
Yeah, so the benefit here is that when you do dimensional jump, the measurement error is like a qubit error because you measure out the qubits.
Yeah.
Yeah, so that gets some, you get a benefit in the dimension. So you don't have to go consider the threshold in a higher dimension, 1 dimension higher. That's the nice part.
Okay.
Well, let's thank Guanyu Zhu again.
Okay.
For the speaker of the morning. And we come back at 10:45 for the second set of talks in the morning.